So continuing, we now have for the next speaker Thiago Guerreiro. He's almost local. He's from PUC in Rio de Janeiro. And then he's going to tell us all about the detection of quantum nature of gravity. So please, Thiago, it's a pleasure for us to have you
Thank you very much. Can you hear me fine? So first of all, thank you, the organizers, for inviting me to this very nice workshop. So I'm from the Pontifical Catholic University of Rio de Janeiro, which is about 5 hours drive from here. Maybe I'll show you a few pictures later on. And today I would like to tell you about our group and can we detect the quantum nature of gravity. I have no definite answers, just some ideas. Okay. So to start with, I like to motivate this with two lines of attack. So we have a tabletop line, okay, which is what we heard from Markus Aspelmeier this morning. So can we beat decoherence to create gravitationally important superpositions? In our case, we have these tiny little masses. I'm an experimental physicist, so we work in the lab. We try to show quantum effects of these levitated nanoparticles. And the second line of attack that I would like to discuss today is, can we show some effects of the effective field theory quantization of Einstein gravity? Okay. Oh, my talk is there. I don't need to look here. So I'm going to start with this one, then I'm going to switch over to the other one. Okay. So we can start with the question, are there predictions from a low energy effective field theory which depart from classical general relativity? And the answer is yes. I mean, we can quantize this theory, it's non-renormalizable, but we can do essentially what is done in quantum optics. Can we measure these predictions? Well, we don't know. Okay, so a few years ago I started to think about this. Many people have thought about this. And the first question that comes to mind is, why should non-classical gravitational wave states exist in nature? Okay, so we know we have examples from cosmology where you can have the universe expands and then you create two-mode squeeze states which are non-classical in a certain sense. But it feels like there's more to that because Einstein gravity is highly non-linear. And in quantum optics, I'm a quantum optics person, so I will think in terms of quantum optics. Non-linear interactions often lead to non-classicality. And in the case of gravity, G is so small that makes one wonder, is gravitational wave decoherence really negligible, or does it affect quantum gravitational wave states? These are interesting questions that we can ask. So a few years ago, I started looking into this. So sort of like a toy model, we could take a gravitational wave detector like LIGO. We can simplify it and have just a single cavity with light. It's stored in the cavity, and the gravitational wave passes by. And now you assume that you can quantize gravitational waves in the very same way that you quantize light. Okay, and you can ask yourself, what is the interaction between the gravitational wave detector, the cavity field, and the quantized gravitational wave mode? And this is very similar to quantum optomechanics, like Marco was mentioning before. Fortunately, this problem has been looked at from a more formal perspective before. There are many papers where you can get this effective quantization from. I took it from Yan-Bei Chen's and Belinda Pang's work back in 2018. And what you get is that the electromagnetic field couples directly to the gravitational wave field. Okay, and it couples via this sort of dispersive optomechanical interaction. So you can assume that quantized gravitational wave states exist in nature. We don't have a theory for the sources of these quantized gravitational waves yet, but they are certainly logically possible. And you can ask what happens if they interact with a detector. Okay, so the first thing you can ask is whether what would happen if a coherent state interacts with your quantum gravitational wave detector. And what you get is you get a sort of unitary evolution. One part has a sort of a squeezing, so your quantum light field gets squeezed by the interaction with the gravitational wave. That turns out to be completely negligible. And the other is a sort of a phase shift. So if you get a gravitational wave in a coherent state interacting with a coherent electromagnetic wave, what you find is precisely a phase imprinted on the optical field due to the interaction with the gravitational wave. And this phase oscillates at the frequency of the gravitational wave, and it has with the amplitude of the strain of the gravitational wave. Okay, So this is exactly what you would expect from classical theory. But now we are in an effective field theory description, so we can ask what would other quantum gravitational wave states look like if they impinged on this detector. So the next example that we looked at was squeeze states, or parametrically amplified gravitational waves, or single mode squeeze states. And you get interesting things. For example, you would have a phase. The signal of your gravitational wave detector could be exponentially enhanced or suppressed depending on the phase of the squeezing, or the squeezing angle of your gravitational wave. Okay. So you can talk to Luca Abraão, my student, who is over there. He knows everything about this. He's a specialist now. You can do also all sorts of interesting exercises. Like, for example, you can consider a thermograviton gravitational wave background impinging on a superposition of different energy eigenstates of the electromagnetic field. You get decoherence, and this agrees with other results that you can find in the literature. For example, this paper by Blancoy or Cano et al. You get that you have a decoherence at a rate which is proportional to the temperature of your gravitational wave background, and sort of scales quadratically with the energy difference between the states in your superposition. Okay. So one thing that I asked in one of these papers, and you can go and read about it, or we can discuss it over the coffee break, is in principle how much information about the quantum gravitational wave state is imprinted in the detector. Okay, so I'm not talking here experiments. This will probably be very complicated to measure in practice, but it's an in principle question. Okay, so for instance, could I reconstruct the whole state of my gravitational wave if I assume that it interacts with that interaction Hamiltonian that I showed before? And as it turns out, is that you can show that the electromagnetic state in your cavity will know about at least the mean expectation values and the covariance matrix of the field quadratures of your quantized gravitational wave field. So in principle, you could set up a non-classicality witness, and you could try to detect the quantum nature of gravitational waves. This is important because, you know, I'm just doing quantum optics here, but instead of photons, I'm considering gravitational waves. We will go through the same, you know, historical turns into showing that the electromagnetic field was quantized. The first person to do that was John Clauser back in '73. So we need experimentally friendly non-classical witnesses of gravitational waves. Okay. This was very emphasized in this recent paper by Don Carney. So you can also look from a semi-classical perspective. Say if your quantized gravitational wave interacts with a classical detector. Okay, this has been done by Parik, Wilczek, and Zahariad recently, and also by other people like Baylock Hu. So you can compute the semi-classical Langevin equation that your detector would have to follow if it interacted with a quantum gravitational or quantized gravitational wave mode. Okay, and you can compute that your gravitational wave detector, these are just two masses here, they interact with your fluctuating gravitational field, and you will get fluctuating force, and you can calculate the spectra of this force. And very interesting, you find if you are in a squeezed gravitational wave, you have an exponential enhancement of this noise. Okay, so this is a sort of a gravitational wave, detecting the quantum nature of gravitational waves through the noise that they impart on a gravitational wave detector. Okay, so we learned about that, and we wanted to transport some of these techniques back into quantum optomechanics. So together with my student Luca Abraão and Pedro Paraguaçu, who is also here, we've looked at what would be the analog problem of two levitated nanoparticles, okay, one next to the other. Now forget a little bit about gravitation. They can be interacting via Coulomb force or whatever mechanism you would like coherent scattering, for example. And if you assume that one of these particles is quantum mechanical and the other is classical, you can show that the quantum interactions between these systems will induce an effective semi-classical dynamics on the semi-classical particle, which has a stochastic force, and this stochastic force depends on h bar, and it sort of characterizes the quantum fluctuations of your quantum particle. Okay, and you can compute the noise correlators and so on. And this is very interesting. You can do stochastic thermodynamics, where now the noise comes from the quantum fluctuations of your system. So there's a poster by Pedro Paraguaçu. You can also talk to him about this over the poster session. So it is interesting that if you assume, we were thinking, right, okay, this is a point where these ideas of quantized gravitational waves, or the observational approach that I was talking, connects to this sort of tabletop approach of trying to show quantum effects in the laboratory. So suppose if we had two masses in superposition, and if we treat one quantum mechanically and the other classically, we can see the quantum mechanical noise of your quantum particle as imparting noise, semi-classical noise on your classical particle. Okay, and interestingly, this force depends on a rate which can be seen as the entanglement rate that Markus Aspelmeier was showing before. So the noise really shows up because these systems, from a quantum mechanical perspective, they are becoming entangled with each other. But from a semi-classical perspective, you perceive this entanglement as local noise in one of the particles. Okay, so this brings me to the second part of my talk, which is the more experimental part, which is, can we beat decoherence to observe gravity-induced entanglement or noise? In other words, can we entangle two particles or observe gravitational-induced entanglement in the laboratory? Okay, I don't have an answer to that question. I'm going to show you a lot of experiments here that we've been doing in Rio. These experiments are done with the motivation of going to this sort of mesoscopic quantum superposition experiments. But what we do in the everyday basis is just we go to the lab and we have a lot of fun by building stuff and trying to make it work. And it doesn't work for most of the year until one time it works, and then we're happy. And we move on to the next idea. I'm being fully honest. Full disclosure. So this is a picture of our levitated nanoparticle. Okay, so we have a laser here. Okay, in our case, it's a 1550 nanometer laser. It's tightly focused, and if you shine this light upon a levitated nanoparticle, maybe you're lucky enough and it drops on the trap, and it's trapped there, and it stays there for as much as you like. Okay, so these systems have a mass of about 10 to the minus 18 kilograms. They are a silica nanoparticle. They're in a solid state. Okay, they can range from radii between 70 to a few hundred nanometers. And once in the trap, this thing acts as a harmonic oscillator, and this harmonic oscillator has frequencies, characteristic frequencies, which range between 50 and 150 kilohertz. Okay, and importantly, these particles are charged, so you can act on them with external electric fields, so you can control their motion. So you can make quantum control of the state of this levitated nanoparticle. So this is sort of like the program of the field, or the steps that you need to conquer in order to achieve quantum mechanical control, and in order to one day, maybe, who knows, be able to show gravitational induced entanglement. So the first thing is you need a ground state, okay, because it's a pure state. That's the simplest pure state you can do. You just remove as much energy as you can from your system, and then you have a pure state. Then you would like to prepare a large delocalization state of your nanoparticle. So in principle, you would like the delocalization to be larger than the size of the particle. Okay, that's very hard. That's producing a very, very squeezed state of the mechanical motion of this particle. And then you would like, ideally, to bring two particles next to each other. They will interact via some interaction, preferably gravity, and then they will entangle with each other. And you would like to see some witness of entanglement that shows that they have interacted via some quantum force, okay, so, or some force that requires quantum mechanics. That's the general idea, or the general program. Of course, we're going to start doing this with these tiny nanoparticles, and then you want to scale up. So once you learn how to do this, you evaluate what you've learned, and you resize your system. You go to larger and larger systems, until eventually you can have a system which has enough gravity to be detectable in the lab. So this program is easier said than done. You have decoherence. The main sources of decoherence are recoil heating from the laser, from the trap that is holding your particle. It scatters light in all random directions. And you also have thermal emission, which also gives you decoherence. Okay, so recoil heating in these nanoparticles has been measured by the Novotny group back in early 2000s. And recoil heating decoherence was observed by the Marcus Arndt group in these molecular interference experiments. As you heat up the molecules, your interference fringes, the visibility goes down and down with temperature. So you need to beat these problems, okay? And our group is investing in a bunch of crazy ideas to try to fix some of these problems. We don't have any definite solution yet. Part of what we are doing currently is trying to catch up with some guys in Europe who already achieved the ground state. So we're going after the ground state as well, which is the step 0 really. But part of what we do is also really trying to come up with different solutions or ideas that nobody is exploring directly in Europe. So because we're in Brazil, we are a bit more relaxed. We can afford that, and we can afford to have, let the Europeans will get there first. We'll get there in our own way. And we will have a lot of fun in the way. So I want to tell you a bit about 3 ideas or 3 experiments. Well, 2 experiments and 1 idea most that it's going on in our lab at the moment. The first is our efforts to reach the ground state. So once you trap these particles, they are highly thermal, okay, and you ideally would like to have a thermal occupation number smaller than 1, okay. These experiments have been achieved in Vienna and ETH using control theory or feedback control, as I'm going to describe now. But it has also been achieved in other groups using cavities. Okay. So the basic observable of your levitated nanoparticle is the scattered light. So the light from the laser scatters away, and it sends in its phase, it contains the position information on your particle. So you measure that, and then you can feed back a force which will counteract the motion of your particle. So you remove energy from your state, okay, until you eventually reach the ground state. And the way we did that in our experiments is through these electrodes here. So the particle sits somewhere in the middle, and you have these 3 electrodes. On the other side, you can see the electrodes. Here, you just see the contacts, okay. And in this way, you have X and Y actuators, which can control the motion of the particle along the transverse plane. And you have also electrodes on the lenses which trap the particle and the lens that collects the scattered light. And that acts along the Z direction. The Z direction is the propagation of the laser here. Okay? And then using clever electronics, you can feed back and remove the energy of your system by control algorithm. So this is typically what you get, the spectrum of the motion of this particle. As you cool it down, the area of the spectrum reduces, and from the area you can extract the temperature of your system. And once you are in the ground state, you essentially see a flat spectrum. You have reached below 1 phonon occupation number. Okay, so these are some preliminary results from our group. You can read them about them in a recent paper, where we reached about 500 millikelvin temperatures of these levitated nanoparticles. Okay, this is still a long way to go from the ground state, but we still have a lot of improvements, known improvements that we are currently pursuing, which will eventually allow us to get closer and closer to the ground state. Okay, this is what the experiment looks like at the moment. This is a bit what Marcus Aspelmeyer showed today this morning, this Heisenberg microscope setup to cool the motion of the levitated nanoparticle. I'm not going to go through the details of all this, but it's sufficient to say that with some improvements that we are currently going on, we estimate that we can reach near ground state temperature for the motion along the 3 axes, X, Y, and Z. Okay, so below 1 occupation number for the Z direction and slightly above for the X and Y, which is very nice. So this is what the setup looks like at the moment. The laser comes in from here. The collection lens here, you have detection of the motion in the forward direction. You have detection of the motion of rotation of the particle, because you also want to know if you have a single particle or if you have an extended object. Sometimes you have 2 particles in your trap. And we also collect the light backwards now. And this light contains the most information about the Z motion of your levitated nanoparticle. so you can actually achieve Heisenberg limited detection of the particle motion, so you can cool it down to near the ground state. Okay. So this brings me to another experiment that we've done in our group. So what I've shown you until now is mostly standard optomechanics using Gaussian beams. We're also using these structured light modes, which are higher order modes of the electromagnetic field. These are solutions of the paraxial equation, which can carry orbital angular momentum. And we can play in the lab, and we can generate arbitrary essentially arbitrary superpositions, at least with these first few modes here. And then this can allow us to manipulate our trapping parameters and to do all sorts of control techniques and funny things on the levitated nanoparticle. So we started playing a little bit with that. And one experiment that we've done was this so-called bottle beam experiment, which is if you have an optical tweezer, the optical force depends primarily on the ratio of the refractive index of the particle to the medium where the particle is. So if your particle has a refractive index which is smaller than the medium, it will be repelled from the maximum of intensity of light, whereas in standard optical tweezers, the particle has a higher refractive index with respect to the medium, and it will be attracted to the highest intensity. So this is standard optical tweezer. This would be a sort of regime where you have a repulsive optical force. So this is like what people in AMO physics call a blue detune or a red detune trap. So we've done this experiment where you take a Gaussian beam and a Laguerre-Gauss mode with P equals 1 and L equals 0. You superpose them with a minus sign, sorry for the typo here, and you create a dip in intensity surrounded by light in all directions. That's what we call a bottle beam. And if you are careful enough and you have a particle with a refractive index which is smaller than the medium where it sits, and you are able to put the particle in this dark spot, then it will stay there, okay, and it will be trapped in the dark. So we've done this experiment in collaboration with Antonio Zellacchetti Curi from the Federal Fluminense University, just across the bay where we are. Okay, and we've reached some interesting results. We've managed to trap a particle here. This has other properties which are interesting for levitated optomechanics. This experiment was done in a liquid medium, so this is not yet quantum optomechanics, but I will get to that in a moment. But we've managed to at least demonstrate the principle and reconstruct the potential where the particle is. I think this is not going to work. This is a video which is very nice. So you can see in the supplementary information of our paper. You have a trapped particle here, and you have some spurious particles which are going around in the sample. And in standard optical tweezers, they would be attracted to the center of the trap. But since this particle is surrounded by light everywhere, these spurious particles will just kick off and bounce because they are repelled by the light. So this sort of protects the particle from the environment, and the particle is there quietly sitting in the dark. Okay. So you can talk to Felipe Almeida, who did the experiment, who is also here, and Ariel Hertz. This might have some applications in biology. You can trap, levitated. You can trap living objects and study their mechanical properties without frying these living objects, which is a problem in standard optical tweezers. So we're pursuing also some experiments in biology. But of course, the main question here is, can we use this thing in levitated optomechanics for quantum experiments in vacuum? So just recently, I started working with a collaborator of mine, Cyril Laplan, from Macquarie University. Well, now he's at Sydney University in Australia. And we asked ourselves the question, can we trap a particle with a negative refractive index or a sort of blue detune trap in the dark spot in vacuum? Okay, so now not in a liquid anymore, but in the vacuum. Okay, and the other question is, does recoil heating of this particle get reduced because now it's trapped in the dark? And does the thermal emission decoherence get reduced because now it's trapped in the dark? So we're working on that at the moment. This is a work in progress. We have some preliminary results using these ytterbium nanocrystals, which have internal resonances, and you can set up your trap such that the laser is blue detuned with respect to these resonances, so you get essentially the same effect as a negative refractive index, even though you are in the vacuum. Okay? And in principle, if you work at the correct wavelength and in the correct regime, then you could trap your particle in the dark, and the recoil heating would be smaller. So that would be, you know, one way of sort of improving significantly the decoherence rates in these levitated optomechanics experiments. So stay tuned, the paper will come out in a couple of weeks, hopefully. We also worked on other weird stuff. We collaborate with Antonio Zelaquete, who is sort of a magician of structured light, okay? He said, we were discussing one day, and he said, what if you could rotate your bottle beam, you know, create a sort of a dynamical trap? And this brings me to the third and last part of my talk, which is fast dynamical control of the particle motion towards the quantum mechanical control. So the idea here is to have not a bottle beam, but to have what we call a saddle beam. So this is a superposition of three modes. So the Gaussian, the Laguerre-Gauss with L equals 2, and the Laguerre-Gauss with L equals -2. And if you tune the constants in the correct way, and if you tune the phases in the correct way, then this beam will rotate. Okay, so the angle in the transverse plane of intensity profile will depend on this phase parameter theta here. Okay, so if you start with beams which have slightly different wavelengths, this phase will change naturally, and this thing will rotate very fast. Okay, so we have studied the dynamics of a particle in such a thing, and we have seen that actually you can stably trap a particle here. So it's like a pole trap, you know, where you achieve dynamical equilibrium, but now dynamical equilibrium comes solely from light forces. There's no electric, you don't need the particle to be electrically charged. Okay. So this is the optical version of dynamic stability. Okay, you have this mechanical version here. You have electrical version, which is a pole trap. You have another, this Kapitsa pendulum, which is also another manifestation of the same phenomenon. Okay? Okay, I'm not going to bother you with these details. These are experimental details. How you produce this, actually, it's not so simple, but also feasible. And it turns out that depending on how you rotate this particle, you have three regimes of operation. You can either trap your particle here in one of the lobes, in which case it will just undergo a rotation in the transverse plane. If you rotate it fast enough, it will be thrown out of the trap, so it doesn't stick. It's just thrown out because of the inertial forces. But if you rotate it fast enough, then it will undergo a complicated motion, which is here at the center. Okay, this is at a certain pressure, so there's a stochasticity in the motion of this particle. But this is a new tool for levitated optomechanics, okay? And now the next thing you can ask is whether you can cool the motion of this levitated nanoparticle in this weird trap. And it turns out that yes, so you can cool it. Okay, what the ground state is not very, I mean, it's well defined, but it's hard to calculate because it's a highly non-harmonic trap. So we don't really know what the ground state looks like. But you can cool the motion of this particle, and you can make it sit quietly in the center of this trap here, okay? So see the poster of Daniel Tandechnik, who is also here, who is the guy who pioneered this saddle beam trap. So here's the basic idea for a quantum experiment, okay? This particle, if this thing is rotating fast enough, this particle sits in a dynamic stable equilibrium. If you make it stop rotating, and you can do that by switching some parameters in your experiment, that can be easily done, I promise you, then this particle will see an inverted potential. Okay? So like Aspelmeyer was mentioning this morning with Oriol Romero's arts group, they have these pioneering ideas of subjecting levitated nanoparticles to inverted potentials. This is one example of how to do it. But here you can do it with the same setup, okay, with the same trap. You have full control over the rotation velocity. You can make it stop very fast. Okay, so you could cool this particle to a very localized state, or sort of close to the ground state, and then stop the rotation, and this particle will, the wave function will expand. Okay, and it will expand very quickly. Okay, and in principle, if you start rotating it back again, you could recover the same particle. Okay, so It's another way of looking at this problem of quickly expanding the wave function and creating interference, and then recovering the particle to sort of do the optomechanical version of a double slit experiment. Okay, and this setup is also highly nonlinear. So you will start to get, if you are in the quantum regime, you will start to get interference fringes because this particle will undergo very nonlinear potential. Okay. So this is still very much in its infancy. We're still looking at the quantum dynamics of the system. We don't know exactly how it scales, how the decoherence rate is. We suspect that it will be a bit smaller than standard Gaussian tweezer experiments because somehow you have less light here in the middle. But we're still undergoing research on that. So, but I'm happy to talk about it later if you want. So just to wrap it up, I hope that with this I can steer some discussion over the coffee. So we have at hand both an observational and a tabletop approach, and much work needs to be done. This is a work in progress. I think this is what this workshop is all about. We need new experimental ideas. Okay, you have to be creative. We have to come up with as many possible different solutions and ideas as we can. And as I was talking to my friend Giorgio Torrieri here, I'm an optimist, and I think that maybe in 15 to 20 years, if we work hard enough and meet every 2 years, we can have some new gravitational physics on the line. So this is the group as it currently looks like. Let me just show you a little bit of advertisement. This is more for the people in Brazil. If you want to come and visit, this is the map. So we are about 6 hours away by car, okay? This is our campus. We have some special guests sometimes. And perhaps the most important and useful information for those who are visiting Rio is that we are only 1 kilometer away from this. So please feel free to visit, and I'm happy to take your questions now.
Questions, guys? I can see Robert is going to one.
Yeah, hi. A very nice talk. I have a naive question about the last thing where it rotates.
Yes.
So just, I want to be clear. So if it doesn't rotate, is it unstable in the trap?
It's unstable in one direction.
Okay.
So let me show you. Yeah, this is the potential. Okay.
If it does not rotate, the potential is at the right?
It will either want to go to this lobe or this lobe. Because
Okay.
the particle will be attracted to either one of these maximum.
Okay, and so if it rotates, you stabilize it,
Yes.
correct?
Yes.
All right, so then the question is, presumably there's some minimal rotation that gives stabilization,
Perfect. Yes.
but there must be some maximal one you can achieve. Can you say something about the ranges?
Yes. Oh, sorry.
The range.
So there are basically, well, there are 3 basic regimes, okay? Either it rotates very slowly and it will just stay in one of these lobes here. You see the scale here is, this Lx is a parameter of the beam, okay? It says basically the beam width, the width of your Gaussian component in the superposition of the light field. So it will be like a merry-go-round. It will stay rotating here. If you start rotating faster, then you have inertial forces that just, throw this thing out. But if it's fast enough, and here I think it's about 200 kilohertz for these parameters, if I'm not mistaken, it will sit in the middle. You see the scale here is much smaller than the scale here in units of this beam parameter width. Yes, I don't know if it's chaotic, but it will be complicated. This is at a high pressure, so you have stochastic forces acting on the particle. At low pressures, it looks something like this. You have this weird spider web shapes, and the spectrum of motion has all sorts of peaks, which are related to the micro motions here. There will be much more information in the poster of Daniel, and he's really, really good at answering these questions. He's got all the numbers figured out, and thank you for the questions. Very nice.
Thank you, Thiago. It's actually about these figures that you're showing there. These lines are supposed to be the particle center of mass position,
Yes.
right? So
Yes.
that's all simulation.
That's simulation, yeah. We haven't done
So-
that experiment yet.
So how do you get these continuous trajectories? What kind of calculation do you do to get?
You just integrate the equations of motion.
Okay. And
Newton's law.
Huh?
This is classical, not quantum.
Ah,
This is Newton's law. This is I'm very proud to have papers in classical physics.
okay. Okay, so I must have missed something because I thought it was a quantum system that you were describing.
No. Yeah, first we're experimentalists, simple-minded experimentalists. First, we're proposing a new trap. We need to trap the particle. So the first thing is to show that it can be stably trapped classically, right? And then we can cool down the motion. Cooling down doesn't mean that you become quantum. It just means that the amplitude of the motion can be reduced by this feedback process that I was describing earlier. And this is what is shown here. But this is just really completely classical. We've only just begun to analyze what the quantum motion will look like, and it's complicated.
Could you just remind me what K is in this figure?
It's the gain of the Kalman matrix algorithm. It's essentially in control theory you have this Kalman algorithm, which is a state estimation. Sorry, I didn't go at all in the details of that. So basically, you measure the position of your particle, and it's a very noisy measurement. And then you use this measurement to estimate the state of your system. And then based on the estimates of the state, you apply a force, which has a proportionality constant, which we call the gain of this feedback. And that's basically what it is. Okay, so it's just to show that there is an optimal gain. And if you're really careful and you put yourself in that, you can really shrink the motion.
Hi Daniel, thanks for the talk. I guess it was the second line of experiments that you presented when you were using Laguerre modes.
Yes.
Now that you have higher order Laguerre modes, how will this affect the focusing that you need to have? Because if you're using only one lenses, and you could possibly need to have like other modes, but you need to control them individually.
That's a very good question.
How will this change your control and experimental aspects of your setup?
Both the bottle beam experiment and the saddle beam experiments, they don't require tight focus. So they are both done, I mean, one is an experiment, the other is a proposal, but they are both considered in a paraxial beam regime. So you don't have really tightly focused beams. So you can use those solutions as your modes, okay? Which is also nice because, light is less concentrated on the particle.
But
I don't know if that answers your question.
No, in a sense, but more the idea that if you're using like a donut mode compared to the size of your particle, and you are complementing it with like a zero mode, then if you are controlling, if I understand correctly, the focus and the position of your lenses, then if you need different, depending on your control, you need to have different focusing for both of them. So how can you control separate focusing for different?
Maybe it will help to tell you how we generate these superpositions. So we have this SLM, it's a spatial light modulator. So you create already at the output of the SLM a mode which on the image plane of your trapping lens will look like the field that you want. So the whole thing travels together already in the correct superposition. It's not that we are superposing them at the beam spot,
So you're not generating 3 different SLMs and then combining them. You're using a single SLM to generate the superposition that you want.
Well, in this one here, it's a complicated way of doing it. We haven't done it yet in the lab, so I cannot answer this question experimentally yet. This is just a proposal. In the bottle beam experiment, it's just one SLM.
Yeah. Okay. Thanks.
That also saves you a lot of work on interferometric stability, which is a good question.
Further questions?
Hello, lovely talk. The basic question I have is how much photon recoil do you expect to get rid of with these techniques? Because that seems like the biggest benefit.
Yes. So, at the expense of maybe having to kill you, I will tell you. No, I'm joking. Because the paper isn't out yet. But, okay. Essentially, to linear order in the transverse plane, you get 0 recoil heating in the bottle beam. To linear order. That's not true along the longitudinal direction, but it's still smaller than the Gaussian. It's because the beam is very flat at the bottom.
So if you still are gas limited by your thermal gas is still your biggest noise source.
Yes, but if you have down to 10 minus 11 millibar, then that's, you know, the gamma of thermal gas is like 10 minus 6 hertz or something like that. So it takes a long time for a molecule to hit your...
Yeah, at what point are you expecting the light to be the dominant noise and the pressure in the vacuum? I mean, is it 10 to the minus 20? I mean...
I think 10 to the minus... yeah, I don't know. I don't know yet. We're still working that out, but...
Further questions, guys? If you're on Zoom, you can just open your mic and go ahead.
I like short talks, that's the problem. Then you have a lot of time for questions.
Yeah. Well, if there isn't any questions, so let's thank the speaker again.
Thank you.